Assalamu alaikum everyone. This is lecture 8 year of the course Control System Engineering. We are discussing in the last week. We actually finished chapter 2, which was modeling the frequency domain. Then chapter 3 is actually state space representation, which is not part of this course, the syllabus of this course. So we are skipping that one and we are moving forward to the next chapter, that is chapter 4, time response. So in the last two chapters, basically chapter 2 and 3, we try to obtain the mathematical modeling. We covered chapter 2, but chapter 3 also same thing, but in a different domain. Okay, so after the mathematical representation of the system, next thing that comes is actually block diagram reduction kind of thing that is covered in chapter 5. But so far we are actually covering things without having a specific direction. What is our actual objective of this course? So that is why chapter 4 rather actually discusses about some of the objectives or the desired behaviors that we are looking for. So we have transient behavior, we have steady state response. So in this one, transient actually the time response actually will be discussed, and the analysis of the transient response as well. So one of the common fact that will be coming in the discussion is the order of the system. So basically, what is order of the system? So one of the things is order of the system. So basically, uh, this is nothing but the order of the power of the S, or the Laplace domain. This is actually power of S of your denominator, so d of s. Okay, so if you have, say, g of s equal to n of s divided by d of s, so the power of the denominator, so say it is s cubed plus 7s square plus 3s plus 5. So this power of s is the order of the system. Okay, so this is one way to define it, or in terms of the differential equation. So if the system is represented in terms of the differential equation, say d square by dt square y of t plus 3 d by dt of yt plus yt equal to xt, something like this. Okay, so here the order of the differential equation is also your order of the system. So this is how you have to define the order of the system. Next thing that comes is actually the system response. So if we try to look at the total response of the system response, So it has two combination of the two. One is called forced response, as well as your natural response. So natural forced response is because of the input, whatever the output you are getting. So if you are applying some input to your system, then whatever the output you are getting, that is actually forced response. And the natural response is the behavior of the system itself. Okay, so whether it is exponentially increasing or decreasing nature. So this is systems behavior. Systems behavior. Okay. Without any input, how it actually behaves. This is what is the natural response. And then we have the definition of the pole. What is the system pole? Okay. Pole of a transfer function. So according to the definition, if the denominators, if you set the denominator equal to 0, then whatever the root you are finding, or actually the Laplace domain, what is the value of the S's you are getting. So those are actually poles of the system. Or if you want to go for the strict definition, then the value of the Laplace transformation variable S that causes the transfer function to become infinity. So it makes sense, isn't it? Because uh, if the roots of d of s is being set, then we can say that if we place say s equal to -2 is one of the roots. So if you set s equal to -2, then your system behavior will be 1 by 0 equal to infinity. So the value of the s that actually produces the d of s to go infinity, that is what is called the pole of a transfer function. Sometimes it may happen that some common factor is also there. Say that we have a pole uh, and 0 at same location s equal to a. Then the rest of the thing may be distinct, like s plus z1, s plus z2 goes on. Similarly, s plus p1, s plus p2 goes on. So now this common factor, even though they'll be actually cancelling each other, we also call this one as a pole by definition. Similarly, this one is also called zero of the system. So the next definition automatically comes is zero of a transfer function. So what is the definition? The definition is mathematically whatever the numericals, the root of the numericals that you are going to get, that will be the value of the SS, that will be your zero of the system. Or in terms of G of S, if N of S is becoming zero, then what we are going to get is your system output will be zero. So the values of the S, according to the definition, the values of the S for which the transfer function becomes zero is called zero of the system. Okay, so these are the basic few definitions. Now, let us look at how, what is the function of the pole of the system, the pole and zero of the first order system. We start with the first order, then gradually we'll move forward to the second order and complicated system. So poles and the zeros of a first order system. Let us begin with an example. Say that poles and zeros of a first order system. So, example. So, say we have g of s equal to s plus 2, s plus divided by s plus 5. So, one of the things is called a pole plot or pole zero plot. Pole zero plot is basically just in the s plane where sigma j omega uh, sigma j omega. So you place the location of the pole. Say here you have 0, 0 is being represented by a circle. So I say it is at -2 and at -5 you actually have a pole. Pole is represented by a cross. Okay, so this is at -5. So this is the convention. So at -2 you have a 0, and at -5 you have a pole. So this is pole zero plot in S plane basically. So this is your S plane. Okay, so this is first thing, pole zero plot. Now, the transfer function, from the transfer function, you can see that there is only one pole, the pole at -5 and 0 at -2. Okay, so let us try to examine how these poles and zeros are contributing to the property of the response. So for that, assume that, or let us apply one test input, say Rs equal to 1 by S, we're trying to apply on that particular system. So this system is S plus 2 divided by S plus 5. This is your G of S. Test input Rs is 1 by S, then Cs we have here. So by applying that step input to the system, we actually want to see how the system behaves. for that. So let us try to write the equation. So if you try to write the equation, then what you have C of S equal to, we know already from the last chapter 2 that RS multiplied by G of S. All the values are known. So basically what we are going to get is S plus 2 divided by S into S plus 5. Now we know the partial fraction expansion. So A by S plus B by S plus 5. So what will be the value of A and B? Very quickly, we're just writing A is basically nothing but S plus 2 divided by S plus 5, S equal to or tends to 0. So then you have 2 by 5. Similarly, B is basically S plus 2 divided by S tends to minus 5. Then what we have is in the numerator we'll have minus 3 and the denominator minus 5, so minus minus cancel, so we'll do 3 by 5. So C of S is becoming 2 by 5 by S plus 3 by 5 by S plus 5. Is it okay? So now this is how the system looks like, the response looks like. So let us try to figure out their corresponding pole zero location, how many poles you have. Don't forget that this S plus 5 is because of your system's pole, and this S is actually because of your input. Okay, so if you try to have the pole zero plot, say you have a pole, this is your input pole at the origin. Okay, so input pole. Then your system have a 0 at minus 2. Say we have a 0 at minus 2. So this is your system 0. System 0. And then we have a pole at minus 5. Okay, so 2, 4, minus 5. Somewhere here, your pole, and this is your system pole. System pole. Actually, that was something else, so you're not considering that. Okay, so now if you look at, compare this with your output. So our output is C of S is basically 2 by 5 by S plus 3 by 5 by S plus 5. Now, if you take inverse Laplace transformation, then you have CT equal to basically 2 by 5 plus 3 by 5 into the power minus 5. Okay, so now let us look at the contribution, or let us look try to find out the property. So this is input pole. So input pole is coming here. Okay, so this portion is because of the input, and we know that if it is coming from the input, then it is actually forced response. So this is forced response. Similarly, this is also forced response. Okay, so what is the contribution of this one? This one is actually this pole. Okay, so this is your system's response. So that is actually natural response. Natural response. Okay, similarly, this is in the time domain, your natural response. And now, what about this one, 2 by 5 or 3 by 5? So this is a combination of basically all the pole and 0. Okay, so they are actually giving this contribution. Okay, so actually you should also, they are also involved in both the cases. So they are also involved to figure out what is the value. So, okay. So now we can summarize what we are actually getting. The first thing is, first conclusion that you can get is actually the better sidewise. So first conclusions. Okay, so first conclusion is system pole is producing, sorry, the input pole generates forced response. Forced response. So this is one. Number two is system poles. System poles generate natural response. So what is number three? Okay, so poles, all the poles here actually in the real axis. So poles in the real axis actually produce exponential response. So poles on the real axis, produces exponential response. Okay, next. Okay, so we can also say so pole at the on the real axis producing exponential response. But what about the location of the pole? So if the location of the pole is here in this direction, or moving farther away from the imaginary axis. So what will be the rate changes in the response? So the smaller the value of the pole, so exponential decay will be slower. So higher the value of the pole, the exponential decay will be faster. So say e to the power minus 10t will be faster in decay, but e to the power minus twice t will be slower in decay. Okay, so the response will be faster for this one. Decay will be faster and the decay will be slower for this one. So this is also, you can add here that the more away from the real axis, the faster the response is. Again, last one is the magnitude. Magnitude or is a actual contribution of the poles and zeros. So the magnitude is the contribution of the poles and zeros. Poles and zeros. Okay, so this is how you have to figure out the properties. With an example, we'll try to figure out the properties. Okay, so whether you have noticed or not, the zero is only contributing to the magnitude, or say it can be contributing the final value as well, because 2/5 is the final value if the t approaches infinity. So the other term will actually vanish to zero. So magnitude is only the contributing factor for the pole, but the behavior, how actually it is behaving, that is actually being contributed by the poles of the system. You have to be careful about it whenever, every time we are dealing with this thing. So the poles are actually the contributing factor in the nature of the behavior. But zero in general, in collaboration with the pole, they actually contribute to the magnitude of the response. Okay, so next thing is once we know that, now we learn try to figure out the what type of response. Sometimes it is difficult to go for the analytical analysis, but if somehow without going to the analytical analysis, you can predict what should be the system behavior just by looking at the poles of the first order system, whether it is possible or not. Let us try to examine that. Okay, so sorry about the handwriting in this class. I'm slightly sick. That is why I'm trying to make it. Also, I have a delay in uploading the video because of my sickness. Okay, so let us try to examine how it actually can, whether by looking at the system, we can predict what is happening in the system. So example 4.1. You have a system, something like this. This is your RS. Still we are assuming 1 by S, that is step response. Then you have S plus 3 divided by S plus 2, S plus 4, and S plus 5. So the system has 1 0 and 3 poles. And your response C of S, this is definitely your G of S. So now how can we predict without going into the analysis, without going for the solution with the value of the coefficients for the partial fraction expansion? Can we directly write the equation for this solution for this one? So we can say that C of S will be something like this. RS into GS. So basically it will be S plus 3 divided by S into S plus 2, S plus 4, and S plus 5. So now can we write the solution of this one? So directly applying the inverse Laplace transformation, now we will have something like this. Just by inspection, inverse Laplace transformation. CT will be K1 plus K2 into the minus twice T plus K3 into the minus twice T, so 40 plus K4 into the power minus 5T. So what should be the value of K1, K2, K3, K4? So that will give you the partial fraction expansion. But we can actually predict the system behavior even without solving it. Okay, so how it will behave. So all of these are actually having exponential decay. And which one will be vanishing first? Definitely e to the power minus 5T will have a higher rate of decreasing. So then 40 will be vanished. Finally, e to the power minus twice 2 will vanish, leaving the final value K1 as out, steady state value. Okay, so by inspection, it is possible to actually figure out what will be the system's behavior eventually. Similarly, you have skill assessment exercise 4.1, which is also very simple. So similar one like this one. So that is why I'm not covering it. I think it will be redundant, so you don't have to do that. I think you can do it by yourself. Very simple. By inspection, you can guess what is happening there. So in the next thing is let us examine a bit more on the first order system so that we can find out the design or the system parameter performance parameters so that they can be easily identified or measured whether the system is a good one, bad one, or how it behaves, how its relationship can be figured out. Okay, so let's consider a generalized one. Okay, so one of the generalized version of it, say that G of S is having a format like A by S plus A. Okay, so in general there should be a 0 and a pole, but we are just taking one generalized version of it. Okay, strictly proper transfer function. Now here we just like G of S block diagram representation will be something like this: A by S plus A. Then you have R of S. Always we use a common test input, that is step input. This is your C of S. So now if you try to solve this one or find out the solution of this one, so let me write it quickly because we already very much familiar with how to deal with the thing. So S plus A. Now you have to go for the partial fraction. So A by S plus B by S plus A. Quickly, A is basically A by S plus A, set S equal to 0. So A by A is 1. And B will be A by S, and S tends to minus A. So basically minus A by A is A by minus A is minus 1. So what we have here is 1 by S plus, sorry, minus 1 by S plus. So now Just take the inverse Laplace transformation. So that will give you inverse Laplace transformation will give you Ct equal to 1 minus e to the minus 18. So this is the solution. Now, according to the previous one, this is your CFT, forced response, and this is your CNT. Okay, so natural response. So total response is a summation of the both. So now the response, if you look at the system response, there is only one parameter available, isn't it? So the only parameter of the response is only parameter is basically A. Okay, so now let us look at the significance of A. Significance of. So what are the significance of A? How actually it controls the behavior of the first order system. Okay, so for doing that, let us assume that the value of the time t, if we take t equal to 1 by A, then what happens to the system response from this formula? So what we are trying to do that there is a, what will happen to the exponential or the natural response. Let us look at that first, then on overall system response. So exponential one will be actually having a e to the minus a t, where t is actually 1 by 8. So e to the minus a into 1 by a. So e to the minus 1, which is nothing but if you calculate it will 0.37. Or now, if you look at the complete response, so Ct will be 1 minus 0.37. So that is basically 6.63. Okay, so now how can we define, based on all these equations that we have covered, how can we define that parameter? So basically, we define that parameter, okay? So based on the three equations that we have figured out, so first of all, the response Ct equal to 1 minus e to the minus 18. So the response equation. Then e to the minus 18 at t equal to 1 by a is basically 0.37, and Ct at t equal to 1 by a is 0.63. So based on these three equations, let us define the three performance specification of the first order system. So three transient response performance specification. Three transient response performance specifications. First one is time constant. Time constant. Okay. So time constant. So time constant is basically 1 by a. So 1 by a is defined as time constant. Defined as time constant. Okay. Now, by looking at this equation, so what does it mean? So first definition that we can give to the time constant is the time it takes for e to the power minus a2 to decay 37% of its initial value. So time taken for e to the power minus a to decay 37% of its initial value. Okay, so this is one definition of the time constant based on this equation. So e to the power 0 was actually 1. Now e to the power 80, while t tends to 1 by a is basically is 0.37. So from 1, it is reducing 0.37. 37% of its initial value. So this is one way to define the time constant. And the second definition is based on this third equation. So the overall response is reaching up to 63% of its final value. So the time taken to time taken for CT to reach 63% of its final value. Final value. Okay, same parameter defining in different ways. So this is how we can define them. Okay, so some other thing is also there. First thing is this is time constant. So 1 by a is having a 1 by a is having the unit s or seconds. Okay, seconds, time constant. So what about the reciprocal of it? So if the reciprocal of 1 by a, that is a, what will be the uh, unit for that? So reciprocal of time constant, reciprocal of time constant. So you can say TC, time constant. So reciprocal of time constant, that is 1 by TC or equal to basically A. So what will be the unit of it? 1 by second. So 1 by second is the unit, or you can also call hertz, isn't it? 1 by second is actually hertz, so frequency. So we can say that A is actually, based on that, we can also define A as exponential frequency. Exponential frequency. So same parameter A, defining in different way, and its behavior. Now it's not yet over. So another thing, another way to figure out what is A is basically, you can take the slope. You can try to find out the slope of the response CT. Okay, so if you take the, so d by dt of 1 minus e to the power minus 80. So if you take the slope of the response CT, then what you can say is 0 minus a, then e to the power minus 80. So basically what we have is a e to the power minus 80. So this is the slope. Now at t equal to 0, at t equal to 0, what is the slope is becoming? So d by dt of CT at t equal to 0 is becoming basically a. So the initial slope of your response is actually the exponential frequency a as well. So what I'm trying to say is that, so your response will be something like this. From the equation that we have derived, we'll have a characteristic curve, something like this. So this is your value 1. Is it okay? So if you draw a initial slope, okay, so if you draw an initial slope of this one, in that case, whatever the slope that you are going to get, initial slope, okay, so approximately, of course, the initial slope of this curve, CT. Okay, so this is, this slope will be your value of, this will give you the value A. Is it okay? So this is how you can also calculate the value of A. So this is your first parameter, basically the first performance specification, the time constant. The time constant PC is basically 1 by A, where A is actually your exponential frequency. Okay, so in different way you can calculate that. And also another thing you can also relate is that whether you noticed or not, your G of S was A by S plus A, isn't it? So what is A is actually, A is nothing but your pole location. Okay. So from not only from this plot you can find it out. So if you know your pole plot, okay, so this is your location, sorry, it has to be paused. So from the pole location as well, you can figure out what will be the value of the A. And correspondingly, if the value of A is higher or lower magnitude wise, then your system response will be faster or slower. Okay? So this is what you can also relate with your pole location with your exponential frequency. Okay, so this is parameter one. So next parameter is called rise time. So next parameter is rise time. Rise time. PR. So what is the definition of the rise time? Definition of the rise time is the time it takes for CT to go, the time it takes for CT to go from 0.1 to 0.9 of its final value. Okay, of its final value. So this is your definition of the rise time. So according to the diagram, what it says, say this is your one, so this is your point. Somewhere here you have a point. Okay, and this is your point one. So from 10% to 19% of the response, the time it takes, that time is called TR. Okay, so it is actually better to say 10% to 90% because of the fact that final value may or may not be one, because you know that even if we give a step input, the output can be something else because of the fact that we have some steady state error. Is it okay? So this is the definition. Is a better definition is to go say that 10% to 90% of the final value, how much time it takes. So we already considering a generalized case, that is CT equal to, say this is your time T1 here, this is T1 and this is T2. So according to the definition, your rise time is basically T2 minus T1. But the formula that we already know, CT is equal to 1 minus CT to the power minus 80. So say CT1 equal to 1 minus e to the minus 81. So CT1 is nothing but 0.1 equal to 1 minus e to the minus 81. Okay, so basically e to the power minus 81 will be 0.9. So minus 81 will be ln 0.9, which is minus 81 equal to minus 0.1053, something like this. But the book approximated that this is almost equal to minus 0.11 for simplicity of the memorization of the derivation. So what we can get is T1 is basically 0.11 by 8. Similarly, we can also calculate the T2. So we can take help of this equation here. So minus a T2 should be equal to ln 0.1. So basically minus 2.3 approximately. So from that one, we can easily calculate that T2 will be 2.3 by A. So your rise time formula TR is T2 minus Q1 equal to 2.3 by A minus 0.11 by A. So it will be actually 2.2 by A. This is the formula for your rise time for first order system. Okay. So next parameter that we have is called settling time. So let me write it here so that you can take the advantage of that figure. So next performance specification is called settling time. Settling time. Settling time PS. So how it is defined? It is whenever your response is within 2% of its final value. So whenever the response is within 2% of its final value. Okay, so what does it mean? Either it may be 98% or 0.98, somewhere here, 98%. Okay. Or, okay, so first order, it is always 98%, so keep it in that way. So 0.98. For the second order system, we'll look at a different way. So plus minus 2%. Well, with that, we'll be discussing later. But within that 0.2% of final value, how much time it takes. So you have to figure out that time. Okay, so that will be your settling time TS. The time it takes to reach the 2% within that 2% of the final value. That is your settling time. So by definition, you can also take the same formula, CT equal to 1 minus e to the power minus 8. So we know that final response will be 0.98, 1 to the power minus 18. So now it should be TS. Okay, so settling time TS. Similarly, TS can also be figured out using that same formula that we have used to figure out the rise time. So ultimately, it will be approximately minus 3.91 by A. Or for simplicity of remembrance, they use so this is plus, so 4 by A. Okay, so this is how you have to figure out the settling time of the first order system. So these are the three parameters here. Now we want to figure out the transfer function of a first order system based on these ideas without say somehow we are given a particular system and we are interested about finding the transfer function of the system. So how can you do that? So analytically, it is not that it is not always possible, as well as it is also not practical. But somehow we can do it by obtaining the step response of the system. So how it is possible? With a step response, as we have seen that in the example that has been given here, with a step response, it is possible to figure out the final value because we know what will be the final value. This is one thing. And also we can figure out the coefficient, the rate of change A. So this information actually helps us to somehow figure out the transfer function. So let us take one example with another generalized transfer function, how actually it can be done. Okay, so let us take one another generalized transfer function. Okay. Not always that it will be A divided by A, S plus A. So it can be some other value, K divided by S plus A. So the pole location is remaining same, only the value at the numerator is changed. So this is another generalized scenario. So we are saying that RS is still the state response, and this is your G of S, and this is your C of S. Now let us look at this, find out the solution of this one very quick, because we are already habituated with this system. So, and based on that, how can we actually find the relations? So now say you have CS equal to, definitely will be something like this, K by S plus. So now we can write in partial fraction manner A by S plus B by S plus. Quickly, your A will be K by S plus A, S equal to 0, so K by A. Similarly, B will be K by S, where S tends to minus A, so minus K by. So we can write that C of S is equal to K by A by S minus K by A by S plus A. Okay. Solution is very, very simple. Now, by looking at this equation, as you can see, if we somehow can identify what is the value of K as well as what is the value of A, then we can easily figure out what will be our system's transfer function K by S plus A. So experimentally or by testing, if we can figure out what is the value of K and A, then figuring out the system's transfer function it will not be complicated. Okay, so this is what we're going to figure out. So let's look at example. This is actually your figure 4.6. Figure 4.6. So if you look at the book, if you need, because my drawing may not be precise, so that is why I'm giving you the number. Just look at it. So what they have given is something like this. They have given a wave shape, something like this, and they have said that the final value here is somewhere here, which is not 1 definitely, and they are saying which is 7.2. No, sorry, 0.72. So we have to figure out what is our transfer functions should look like. Okay. So first of all, what do we know? The final value here is 0.72. So this is what we know, final value. And we also know by definition, the time constant is the time it takes to go 63% of its final value. Final value. Okay, so that will give you time constant, which is nothing but 1 by 8. So we have to figure out that time. The time it takes to go 63% of its final value. So time takes to reach 63% of the final value. So final value is 0.75. So 63% of 0.72 is basically 0.63 into 0.72, which is I think 0.45. So we have to figure out what is 0.45 from that graph, 0.45. And that corresponding time you have to figure out. So if you look at books example, they are saying that this time is basically 0.1. Okay, so 0.13. 0.1. Okay, so once you know the time, 0.13, which is by definition the time it takes to reach the 63%. So basically this is your TC, 0.13. So what is the value A? A is basically 1 by TC. Okay, so 1 by 0.13. So basically 7.7. So once we know the value of the A, then the rest of the thing is left is to find the value of the K. And now, what is the final value? What is the formula for the final value? So if you look at this equation, and you take inverse Laplace transformation of this one, then you can easily find out what is your final value. So Ct is nothing but k by a minus k by a to the minus 18. So this will be vanishing as t approaches infinity. So this is your final value, k by a. So this is your final value. So we already know what is our final value. Final value of the problem is 0.72. What does it mean is k by a is basically 0.72. Is it okay? We already know the value of a. So k is basically 0.72 into a, that is 0.72, 72 into 7.7. So which is 5.54. So now we know what is the value of A, we know what is the value of K. So we can easily say that our system by inspect or estimation, our transfer function should be something like this. G of S equal to 5.54 divided by S plus 7.7. Okay, so the plot that has been actually obtained, this is estimated and actually obtained based on which transfer function, figure 4.6 was actually G of S equal to 5 by S plus 7. So as you can see, they're almost comparable. So by having that step response, you can actually predict very closely what should be the approximate transfer function of your first order system. So it's not that complicated. So, but the fact is that you have to go in detail. You have to go into the basic derivation, everything, and understanding. If it is clear to you, on that case, it will be relatively easier for you to actually figure out how to find out the system from the response itself, the state response period. But it is not always easy because of the fact that you don't know, maybe the system itself has some feedback or closed loop, having the closed loop format, or having some parameter that is difficult to identify from the outside. So in that case, still you can have a prediction of the system behavior, and based on that prediction, you can actually predict closely where the system pole zero may be, and based on that value of the k and a, we can have an approximate model, which is may not be 100% correct, but it will be very close, so that you can have your intuitive idea about the system. Okay, so this is one way from graphically. How can we find out the system's transfer function? Then you have your skill assessment exercise. Skill assessment exercise, it is relatively easier, 4.2. What they have given you is the transfer function G of S equal to 50 by S plus 50. Okay. So basically, this parameter is A. So now what they're asking is to find out the time constant. So the TC is basically 1 by A. So 1 by 50.02. And then what is the time constant TS? Time constant TS, the settling time. By definition, it is 4 by A, according to our derivation basically. So 4 by 50. So basically 0.08. Next thing they wanted to figure out is the rise time. So TR is basically 2.2 by A. And then you can figure out, so 4 by 50, so 2.2 by 50, and that is your 0.044. So all these are times. So this is a second. So this is how you have to figure out the first order system, their corresponding transfer function, as well as their system performance specifications. So all these things can be figured out in this way. So it's not that complicated. So one question I want to give you, whether it is possible to have some oscillatory response from a first order system like this, oscillatory response. So that will be one question to answer for you from the first order system, or it will always have a response that will have something like this. Okay, so this is one thing. Even though I'm not sure whether how much time has elapsed, but I think it's almost 1 hour or closer to that. So if we start another topic, it will be difficult to finish that one. I think it will take more than 20 minutes, almost 20 minutes. So I think let me stop here. Also, you're complaining about 3 classes, so maybe time, if it is reduced a bit, that will be helpful for you. So far, whatever we have discussed in this chapter is basically from Article 2.1, sorry, 4.1 to 4.3. And next, whatever we'll be discussing is your Article 4.4 in the next class, hopefully, second order systems introduction. So introduction to second order system introduction. Okay, so things will not be as simple as it was for the first order system. For the second order system, basically, a lot of different forms of response will be possible. So things will be getting interesting, as well as mathematically very interesting. So that is what we are hoping to cover in the coming lecture, inshallah. So let me stop the class here. Okay, see you in the next class, inshallah.